Towards the end of 2024, Prusa Research made an announcement to much excitement from the community, a fully enclosed CoreXY consumer 3D printer, the Prusa Core One. I ordered mine straight away because I was quite excited to take a closer look, so that means no special treatment or special pricing. I just bought it in the queue with everyone else. Once it arrived, I filmed a little unboxing, which maybe we'll take a look at another time. I then printed a couple of parts, like the cauliflower, benchy, and a little Prusa label, and then started with a full disassembly, which is what we'll be taking a look at today. I'll show you the full process, why I found certain bits interesting, and at the end I'll give you my opinions on what I thought about the overall build quality of the Prusa Core One. This video is not sponsored by any external company, but it is supported by my own shop, vector3d.shop, so if you're grateful for what I've done here, want to see more like it, or just interested in some cool 3D printing gear, please consider supporting by grabbing something from the shop today. I started off the disassembly by unplugging it and then doing the reverse of the kind of quick start assembly manual, which basically just involves removing the LCD display. I should let you know that while doing this, I have absolutely no guide or instructions or anything, other than what came in the box with the printer like everyone else. I'm doing this for my own interest and so that you don't have to. You can take a look inside your machine without the risk of damaging something because I'm doing it for you. After dealing with the LCD, next it was onto the hinges in two parts, and you do have to push the pin out of the hinge, so a very small Allen key will get that done quite easily. Overall, this small injection molded hinge does seem like a bit of a weird choice, so maybe this is one we can ask the Prusa team and find out what the real reason is. Next, I moved on to the panels, which are held on with these small nylon rivets. These are in two parts. You have the pin and the prongs. You push the pin in through the prongs, it separates the prongs and holds everything together. Compared to screws, nylon rivets can provide a number of advantages, such as being cost-effective, corrosion resistant, they're very easy to install, they have some potential vibration damping effects which can be useful on these larger panels, and they of course have a reduced risk of over-tightening since you just press them in and that's it. However, pushing them out with your fingers is a little bit painful, so a little tool would be quite helpful here. Some varieties of these rivets are sometimes single use, although I've managed to reuse these ones, so maybe these ones can be reused, but maybe not infinitely. These rivets are used quite extensively, holding all of the exterior panels onto the main frame. When it comes to the structural parts of the machine though, like the external frame, the gantry plate and the bottom plate, these are all screwed together like onto the frame, so like structurally, the nylon rivets aren't really there for contributing strength, they're just holding the external panels onto the rest of the frame. As I'm getting the side panel out, you can see that there's also the filament sensor attached to that, so that has to come out separately later. And then I swiftly move on to the opposite side panel, again with those rivets. These two side panels are mostly the same, for example the overall size and hole patterns. They're both made from 1.2mm steel and weigh around 1.5 kilos each. But the side with the filament sensor, PTFE pass-through and spool holder do have a couple of extra holes. Moving around to the back, guess what? More rivets! As with the other panels, there's 3 rivets along the bottom edge which you have to turn the printer over to get to. For some reason, I expected this whole electronics panel to just come out. Of course, there was absolutely no chance that was ever going to happen because there's loads of stuff attached. So instead, it's time to start removing parts of the frame because the screws are visible and I could remove them. The fastener situation on the Core One is a little bit weird. Obviously, we had the rivets for the outer panels, that kind of makes sense. But then as we start to disassemble more, there is a combination of hex head screws and Torx screws. My guess here is that it's one of 3 options. Either some sort of certification safety reason, maybe some sort of serviceability where hex is for screws you should be dealing with and Torx is for ones you shouldn't, and maybe the third option is that they can just sustain a little bit more torque before being damaged. I don't know, it's not something I've tested. I'll ask the Prusa team and see if they have a good answer for me. Either way, all the tools that you would need to remove these screws are included, so I think that's quite good. The frame is one of the key areas that makes this machine quite different to how others are constructed, and therefore it provided a key point of interest for me when disassembling, so let's take a look at how they've done it. There are 2 different size pieces, a short piece and that makes the perimeter around the top and bottom, and then the longer pieces which go from bottom to top. They're manufactured from 1mm thick steel and powder coated in the classic Prusa sparkly black. The way they assemble together is quite clever. You have these little folded tabs at the end of each of the pieces, and in those tabs is a little boss to allow for a good strong thread. You pass the screw through one part, into the thread, tighten it down, and that's those two pieces joined. The reason I think this is particularly clever is not only are all the joints completely flush, the bends in the sheet metal add to its rigidity quite significantly, especially when assembled together into their final frame shape. All the screws are identical and you only need 3 screws per joint. Overall, a very efficient design for both manufacture and assembly. Moving on now, I continue to try and tackle this electronics panel and I can't for the life of me work out where it's still screwed in. And then I notice this little bit in the middle where there's like a hole and I poke it and whatnot. I can't find any screws attaching to it until I finally find some on the inside poking outwards. After carefully removing those 2 screws, I eventually find that it is just an electronics cover panel. However, I did also identify that one of the wires seems to have been pinched in the assembly process. I suspect literally just tying down that zip tie a little bit tighter probably would have prevented that. With the cover panel removed, I found this one last screw connecting the electronics panel to the gantry. I then decided that the gantry was hopefully the next thing that needed to come out, so I removed some of these other frame pieces that are supporting the gantry in order to try and do that. Watching this back now, it's kind of clear that this is probably not the correct process for doing this, but as I mentioned, I had no instructions and just had to go step by step and do what I could. It was at this point that I remembered wires exist and everything is still connected to the control board, so it was time to open that up and start looking at how stuff's connected. The first and larger of the 2 control boards found in this enclosure is the X-Buddy controller, which is the same one used in the Prusa Mark IV. This main board uses an ARM STM32F4 microcontroller. All of the connectors that you see around the board in the off-white colour are Molex ClickMate. Going clockwise around the board, starting from the top left corner, we have the X, Y, Z left and Z right motors, MMU, a small battery, LCD in orange, Nextruder, accelerometer, power panic, power input, heated bed input, Ethernet LAN, ESP connector, I2C, USB, and temperature sensor. In the middle, we also have the heated bed output and bed temperature sensor. We'll see a little later on how the 3 Z motors are controlled. The second and smaller PCB in the enclosure is the X-Buddy extension board, and this uses an STM32H5 microcontroller. Again, going clockwise from the top left corner, we have extension, temperature, filament, fan 1, fan 2, fan 3, WLED, RGB WLED, PubCan, X-Buddy, and MMU connectors, as well as a USB on the left-hand side. With all those wires removed, I then fish out the fan wires through the gantry plate, and then the gantry plate can be removed from the rest of the printer, and we'll take a look at that in detail in a moment. While I'm looking for somewhere to put the gantry, if you'd like to support me, why not check out vector3d.shop. My aim is to create cool products for you and support small businesses and independent content creators from around the globe. For now, I'm continuing with that electronics panel, so I'm feeding the bed wires back through, and that should leave the bed free to move. Now I'm going to try and remove the control board and the power supply from the panel. The printed part I've removed there also contains a sticker which is the NFC antenna, which has to be gently unplugged from the control board. The label says Pulse W3509. Moving over to the power supply, there is also a cover over the terminals here, which is of course very sensible, but there's nothing to very easily grab at that cover to actually remove it. So I had to stick a Allen key behind it and sort of leverage it against the back of the printed part. So that was a bit of a difficult bit to get out, but I managed eventually. At this point, it was a matter of removing those wires that are going down into the basement of the printer, because those are kind of at the moment what's connecting that electronics panel to that base part. The cables that are going down here are for the LCD, there's 3 Z motors, and an earth cable to connect all the metal parts together. Once those are all unplugged and fished out, we can finally remove that electronics panel from the rest of the printer. And with that out of the way, we can remove these extra 4 frame pieces which surround the base and also hide away this one little PCB which I wasn't expecting to find. This is a motor splitter. What this does is split the signal from one of the stepper drivers for the Z-axis and shares it to all 3 stepper motors. It doesn't have any kind of special microprocessor or anything, it's not doing any kind of signal changes, it's literally just connecting all 3 stepper motors to a single motor driver. Now on the bed assembly, the first thing I tried to do was remove the central bed and bed plate from these corner parts that do the motion up and down. Just a few screws to remove that, and it's quite easy to get out. Interestingly, on this machine, while there are 3 lead screws, there's only 2 Z rods. I think this is probably fine, seeing as all the load is taken by the lead screws, and the rods just allow for correct alignment as it moves. In this case, I think 2 rods is sufficient to do that job. After removing the Z rods, which is very easy, now we'll take a look at the Z motors, and we're going to have a little pause here because I found these one of the most interesting parts of the printer. I started to think something would be different when I saw that the hole pattern for the motors didn't seem to be the right size for NEMA 17. The second thing that was weird is, as I was unscrewing them, they weren't loose as they would be if they were straight into a metal thread, so they clearly had some resistance, like a nylock nut or something. And then once I finally got them unscrewed, I realised quite what was going on. This is rather interesting. Because of the step-like motion that you get from a stepper motor, this causes quite a bit of vibration. You attach these to a large flat plate, and what you essentially would create is a speaker, resulting in a rather loud 3D printer. So what you need to do is find some way to take those vibrations from the motor and make sure they don't get to the plate. So what you've got here is a 3D printed decoupler. Immediately above the motor there's an acrylic spacer, and then the 3D printed part goes on top. And all of that is rigidly fixed to the motor with the 4 screws that you see here. Due to the shape of the acrylic spacer, there's a gap between the printed part and the motor in the central region. It's that central area where this series of thin beams allows for some flexibility in the printed part. The reason I think the design is quite clever is not only is it 3D printed, but it allows for flexibility in such a way that reduces noise, whilst also being stiff enough to still transfer the torque of the motor through the lead screw and provide that Z-axis stability that's required for 3D printing. I would have a slight concern that the overall Z deformation would increase as the weight of a print onto these dampers increases. However, the amount of weight required to make a significant difference is probably quite high relative to the overall precision of the machine. Once the other 2 motors are removed from that plate is completely empty and finished. Now we can move on to the bed, where we start with the plate that holds the LED in place. It does have a little diffuser on it, and then below is just a kind of sticker-based LED PCB. The way this is assembled means we're not really relying too much on that adhesive to keep the LED in place, but nevertheless I prefer to see a PCB that can be screwed in or otherwise attached and detached as necessary for maintenance. For any existing Prusa users, this bed will be very familiar, as it's the same design used on the Mark IV. Same screws, same mounting things for thermal expansion, pretty much the same everything. It's just the metal plate underneath that's different. Because the LED can't be detached, I had to remove the sleeve in order to separate the bed from the steel plate. Moving on to the LCD display, this is again a really nice simple design. Just a few screws clamp all 3 parts together. As you can see from the silk screen, this is the same LCD as they use on their other printers. After removing the power supply and electronics enclosure from that rear electronics panel, I've flipped it over to check out the fans on the back. These are 60mm 4-pin PWM fans, but there's no other specification, so I'm not too sure on the other details. There's also a thermistor attached back here, which allows for temperature sensing of the chamber. Now that we've finished with the electronics panel, let's move on to the gantry with the Hotend and Nextruder malarkey. Since I never owned a Mark IV, this is my first time seeing the Nextruder, and I was reasonably impressed. But disassembly was a bit confusing. I started by trying to remove as many of the covering panels as I could, just to hopefully get access to more things underneath and see more about how the whole thing was put together. After the cover panels, I moved on to the fans, as they seem to be the most accessible thing to remove, and all these connectors very nicely clip in, so it's quite easy to access and remove things as you go. From there, I managed to remove the hot end, and then started on the actual extruder panel itself. Now, it's not recommended, I don't think, to disassemble this, but I will have to do it, so here we go. Turns out quite easy to disassemble. Presumably the assembly is a bit more difficult to get just right. I'll remind you again quickly, I don't have any instructions. That's why the order in which I do things might look a bit weird, because I'm just trying things as I go. I want to stop now for a second to focus on this CNC machined piece, which is quite an impressive feat, given the number of things that it does. This part forms basically the core of the Hotend and Nextruder assembly, but would typically probably be named the cold side. Moving down from the top though, we have quite a few different functions, starting with the filament tension lever, and then the filament sensor with this little PCB on the left hand side. Below that we have the kind of gluey area, which is where the strain gauge attaches for nozzle probing and extrusion force sensing. And then in this region at the bottom we obviously have our fin array where the fan attaches, and that's for dissipating heat from the hot end. At the bottom we have the location where the thermistor goes in, which can be used to detect heat creep or fan failure. On the right hand side we have the two thumb screws which attach the hot end, and off towards the bottom that's obviously the hot end, and that pushes up into that region too. Quite a lot of stuff, all for one part. With the hot end and cold side piece out, it was now pretty easy to remove all of the wires and the connectors that attach to the tool head board. These connectors are really good, by the way. Even when there's loads of wires, it's still very easy to insert and remove them, which is great. So this is the tool head board. It's also affectionately known as the love board for some reason. I don't know. Around the edge, we obviously have the standard clickmate connectors, and then maybe two components of interest. At the top right, we have the HX717. This converts the analog signal of the load cell to a digital signal. So it's a DAC, or rather the opposite of a DAC. And then in the middle of the board, we have an S490AB, which is for RS485 communication, which is a type of serial communication, which is presumably to communicate the load cell data back to the controller. With all the fancy electronics out of the way, we're just left with a gantry and the skeleton for the Hotend and Nextruder assembly. Some of these printed parts are still pretty impressive just on their own accord. I think they're quite complex parts, and it's interesting to find that they printed them on this kind of weird angle in order to get all the features to print and look great. With the extruder all out the way, I can now take a closer look at this carriage plate. It's CNC machined and did catch my eye somewhat, but we'll discuss why a little bit later on. Next, as I was removing this beefy end stop switch from the CoreXY Gantry, I realised it had this weird resistor soldered to the back. And then realised it's on another antenna too, and realised it's probably for some sort of EMC certification or regulation, because if those wires are not connected, they're basically two long wires sticking out and they will just act like antennas. While I've been chatting about antennas, you can see I've made some progress removing the CoreXY motion components, namely the motors and idlers, which is basically just a bunch of printed parts, bearings and stepper motors. Next, it was the LED at the front, which does the chamber illumination, which is removable, kind of, but still stuck to a piece of metal. When it comes to these motors and idlers, I think the most special thing here is that all of the idler pieces are exactly the same. So all identical bearings, pulleys, sizes, so it doesn't matter pretty much which one goes where, they're all identical. Into the final stretch of disassembly now, as we take a look at the motion components of the CoreXY Gantry. This lot is pretty much all steel, with the exception of the CNC'd components. I know quite a few of you will be interested in the weights, so I've weighed a bunch of these motion components so you can get an idea of how much mass is moving around on this gantry. The linear rail used on the x-axis is a 12mm size, while the rods on the y-axis are 10mm. The bearings for the rods are actually two smaller ones rather than a single long bearing. The square tube that holds the linear rail is 20 by 10mm with a 1mm thick wall, but they seem to have done some interesting processing with the kind of drilling or hole creation in order to make the holes deeper than the thickness of the material. I don't know quite how they've done that, maybe another question for the Prusa team. Before I cover my opinions on the hardware, do you remember I brought up that CNC part and something looked a little bit interesting? Well, I think they all look like they could be 3D printed. This is either a side effect of having an engineering team that's very used to designing 3D printed parts, or they've been prototyped using FDM, and then the end result ends up just being like the FDM part, but stronger. I'll be posing this question and the others proposed in the video to the Prusa team, and we'll hear back in the next video about what their answers are to those questions. I could probably spend another hour looking at and discussing the general hardware and build quality of this machine. But for today, I'm going to try and keep it simple, focus on the Core One and the things that I know about the printer from what I've done so far. And remember, I've not really used this machine at all from a user perspective. I've done like 2 prints in the first day and then immediately disassembled. I've also not watched any reviews, so I have no idea what other people have picked up or commented on when it comes to this specific machine. So these are my impressions of what I know. From the surface level, just looking in, having general impressions on what you see as you use the printer. Some things like nylon rivets and plastic panels may feel a bit cheap compared to things like glass and screws that we've seen on other machines. It's not without good reason when it comes to things like optimization and putting the money where it's most important. But once you start digging, all you'll really find is well designed, well manufactured and high quality parts. It's a little bit of a shame really, from my perspective, that many people won't dig deep enough to find the coolest stuff in this machine, because it's all on the inside, and unless you literally take it apart like I have, you might never see it. and instead people may get stuck commenting or criticising on the facade, the obvious things on the top, like the rivets and plastic panels. You may have also noticed as we went along that a number of the parts in this printer also belong to the other printers in the Prusa family, like the Mark 4S. And for good reason. There's a comprehensive upgrade kit to go from Mark 4S to the Core One. The question is, does that upgrade path now compromise the capabilities of the Core One because of reusing parts from that machine? Ultimately, it's hard to say because we don't know what the specific objectives were of this machine when it was designed. If the objective is to meet exactly what it has done, then we can argue that nothing has been compromised. But what we do know is that by having those existing parts used in a second machine, they've significantly reduced their own risk, and from a user perspective, this means fewer surprises, especially of the bad kind, like failure of parts, since the things that they've used again are well-known quantities. They're established within production and support, and we know that they work and have been for a long time. The downside here is that it can make this new printer feel less exciting, because it's not 100% all new. But I'd warn against letting that excitement drive a purchase decision, because it's a short-term feeling on a long-term purchase. If you want a printer that just works, ultimately established designs that we know are good are going to be a stronger foundation for success than stuff that's just fancy, new and shiny. If you'd like to support my work here, which I can assure you has taken a bloomin' long time, please consider making a purchase from vector3d.shop. Thank you very much for watching, and if you'll excuse me, I've got a printer to go and assemble because it's been dismantled for maybe like 2 weeks or so now, and I think I might have forgotten how to put it back together again.